Greetings, welcome to this new video about superposition theorem. Solve the problem number 14. In this video, I will demonstrate the application of the superposition method to solve a problem, and I will guide you through the step-by-step process of using superposition to solve the problem at hand. Let's consider this network consisting of 5 resistors labeled R1 through R5, as well as 3 independent sources. The question now is to use a superposition method to find the voltage Vx across the resistor R3. Let's move on to the solution. First, we begin by identifying each independent source in this circuit. This step provides a clear understanding of the sources that will be analyzed separately. In this circuit, we can observe 3 independent sources, 1 independent current source Is, and 2 independent voltage sources Va and Vb. Next, we proceed to deactivate all but 1 independent source in the circuit. This involves replacing the inactive voltage source with a short circuit, which means 0 voltage, and the current source with an open circuit, which means 0 current. First, let's begin by activating the independent voltage source Va and deactivating the independent current source Is and the independent voltage source Vb, which will be replaced respectively by an open circuit and a short circuit. The next step is to solve the circuit using conventional techniques, and I will consider IT is the total current in this circuit, and I is the current through the resistor R3. The total resistance of this circuit is given by R4 parallel to R5 in series with R3, all in parallel to R2, and all in series with R1. I will consider RA to represent the parallel combination of R4 and R5 in series with the R3. That means RA is equal to R4 times R5 over R4 plus R5 plus R3. We get RA is equal to 22 ohms. And I will consider RB to represent the parallel combination of RA and R2. That means RB is equal to RA times R2 over RA plus R2. We get RB is equal to 16.09 ohms. And the total resistance is equal to RB plus R1. If we replace RB and R1 with their numerical values, we obtain RT is equal to 46.09 ohms. The total current can be calculated by VA over RT according to Ohm's law. And if we replace VA and RT with their numerical values, we obtain IT is equal to 1.95 amps. In order to calculate the current I through the resistor R3, I'm going to use the current division rule. That means I is equal to R2 over RA plus R2 times IT. And if we replace the current and the resistors with their numerical values, we obtain I is equal to 1.428 amps. The voltage V1 across the resistor R3 can be calculated using Ohm's law. That means V1 is equal to R3 times I. And if we replace R3 and I with their numerical values, we obtain V1 is equal to 14.28 volt. Now, let's consider the independent current source Is active and the independent voltage sources Va and Vb inactive, which will be replaced by short circuits. I will consider I is the current through the resistor R3, and I will consider RA to represent the parallel combination of R4 and R5. That means RA is equal to 12 ohms. And RB to represent the parallel combination of R1 and R2 in series with R3. That means RB is equal to R1 times R2 over R1 plus R2 plus R3. We get 30 ohms. In order to calculate the current I, I'm going to use the current division rule. That means I is equal to negative RA over RA plus RB times IS. And if we replace the resistors and the current with their numerical values, we obtain IA is equal to negative 1.714 amps. According to Ohm's law, the voltage V2 across the resistor R3 is given by R3 times I. And if we replace R3 and I with their numerical values, we obtain V2 is equal to negative 17.14 volt. Now, let's consider the independent voltage source VB active and the independent voltage source VA inactive and the independent current source IS inactive, which will be replaced respectively by a short circuit and an open circuit. I will consider I is the current through the resistor R3 and IT is the total current in this circuit. The total resistance in this circuit is given by R1 parallel to R2 in series with R3, all in parallel to R4 in series with R5. And I will consider RA to represent the parallel combination of R1 and R2 in series with R3. That means RA is equal to R1 times R2 over R1 plus R2 plus R3. We get RA is equal to 30 ohms. And I will consider RB to represent the parallel combination of RA and R4. That means RB is equal to RA times R4 over RA plus R4. We get 15 ohms. The total resistance RT is equal to RB plus R5. We get 35 ohms. Now, the total current IT is equal to VB over RT. And if we replace VB over RT, we get IT is equal to 1.14 amps. In order to calculate the current I, I'm going to use the current division rule. That means I is equal to negative R4 over RA plus R4 times IT. And if we replace the resistors and the current with their numerical values, we obtain I is equal to negative 0.571 amps. According to Ohm's law, the voltage V3 across the resistor R3 is given by R3 times I. And if we replace R3 and I with their numerical values, we obtain V3 is equal to negative 5.71 volt. After completing the analysis for each independent source while treating the others as turned off, the next step is to combine the results algebraically. This process enables us to determine the overall circuit response. That means the voltage Vx across the resistor R3 is given by V1 plus V2 plus V3. And if we replace V1, V2, and V3 with their numerical values, we obtain Vx is equal to negative 8.57 volt. After we finish the calculation, we conduct a simulation using a SPICE simulator in order to verify our results. Now let's proceed to the SPICE environment. Here is our network drawn in SPICE simulator. This is the independent voltage source VA, the independent current source IS, and the independent voltage source VB, a resistor R1, R2, R3, R4, and R5, and I connect here a voltmeter in order to measure the voltage Vx across the resistor R3. Let's move on to analysis. DC analysis, calculate nodal voltage. We can see here that Vx is equal to negative 8.57 volt. After completing the circuit simulation, we can clearly observe the similarity between the simulation and calculation results. This serves a validation of our work. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. Take care and bye-bye.